Welcome everyone, and thank you for joining my talk today. My name is Przemysław Pardel, and I'm an assistant professor at the University of Rzeszów, where I specialize in medical data analysis. My work centers on identifying pathological patterns in clinical datasets and enhancing the interpretation of medical images to support decision making. The title of my presentation is Decision Support in Extreme Environments, Applying Medical Data Pathology Detection and Multi-Criteria Conflict Resolution to Analog Space Missions. I will explore how decision-making methods developed for medical environments can be adapted to support astronauts during analog space missions. I had the privilege of completing an international training program where I served as both commander and habitat system officer during the 48th analog lunar mission at the Analog Astronaut Training Center. This hands-on experience reinforces the relevance of my research and demonstrates its applicability in real mission scenarios. Thank you so much, Agata and the team, for giving me this unique opportunity. Analog space missions are Earth-based simulations that replicate the conditions of space exploration. They are essential for preparing astronauts, testing equipment, and conducting research on human behavior in isolated and extreme environments. These missions allows us to study how decisions are made when resources are limited and time is crucial. Understanding this context helps us appreciate the challenges faced during real space missions. Medical environments and analog space missions share several decision-making challenges. In both cases, professionals must take quick decisions based on incomplete, inconsistent, or noisy data. They also face conflicting objectives, such as maintaining health, completing tasks, or managing limited resources. By applying structured decision support systems from medicine, we can enhance the effectiveness of decision-making in space analog missions. Extreme environments such as analog space missions present unique decision-making challenges. Decisions often need to be made quickly, as I mentioned before, under high uncertainty and time pressure. Data sources may be limited, degraded, or noisy, making it difficult to access the situation accurately. Astronauts must balance conflicting objectives, completing mission tasks, preserving resources, and ensuring crew health and safety. These conditions require robust decision support systems that can operate under stress and ambiguity. In medical context, data pathology refers to anomalies or inconsistencies in data. This can include missing patient records, contradictory lab results, or sensor malfunctions. For example, a heart rate monitor may report values that are physiologically impossible, or lab tests may yield conflicting results. Such pathologies complicate diagnosis and treatment and require careful handling to avoid incorrect decisions. Understanding and detecting data pathology is a critical step for reliable decision support systems. There are several methods for detecting data pathology in medical datasets. Statistical anomaly detection can identify outliers that deviate significantly from expected norms. Rules-based validation uses predefined logic to flag inconsistencies. Machine learning classifiers can be trained to recognize patterns associated with faulty data, and temporal consistency check ensure that data evolves logically over time. These techniques help ensure that decisions are based on reliable and interpretable data. In many real-world scenarios, decisions must be made by balancing multiple conflicting objectives. This is especially true in extreme environments, where trade-offs are inevitable. Multi-criteria decision-making provides structured framework to evaluate options based on several criteria. For example, astronauts may need to choose between completing a task quickly or ensuring it is done with a high accuracy, or between preserving crew health and achieving mission goals. These frameworks helps make rational decisions under pressure. In medical decision-making, multi-criteria approaches are used to handle complex solutions. Doctors often work with incomplete or conflicting data and must weigh the effectiveness of treatment against potential side effects. They also need to prioritize patients' outcome while managing limited resources such as beds or medications. Tools like decisions matrices and scoring models helps clinicians evaluate options systematically and make informed choices. The same multi-criteria decision-making methods used in medicine can be adapted to analog space missions. Astronauts face similar constraints. Decision support system can help prioritize tasks, manage risk, and maintain crew health. These methods can be integrated with mission planning tools to enhance autonomy resilience. By transferring proven medical decision frameworks to space context, we can improve mission outcomes and safety. This slide presents a hypothetical scenario during an EVA. A crew member reports symptoms of discomfort, raising concerns about their health and safety. The situation is complicated by limited diagnostic tools and conflicting sensor data, making it difficult to assess the severity of the issue. Additionally, the EVA is time-sensitive, with missions that schedule under pressure. The commander must choose between three options: continuing the EVA, aborting it, or initiating treatment on-site. Each option carries trade-offs in terms of crew health, mission success, resource usage, and time constraints. This scenario illustrates the importance of structured decision-making under uncertainty, where tools like MCDA can support rational and transparent choices. The decision-making process begins with detecting data pathology, identifying anomalies in sensor readings. Next, the team validates critical data points using redundancy and expert judgment. A multi-criteria decision model is applied, weighting crew health, mission objectives, and resource constraints. Options are evaluated: should the EVA continue, be aborted, or should treatment begin immediately? Finally, rational document for future analysis and accountability is prepared. In analog missions, decision-making criteria and their weights are predefined by mission planners. Crew health risk is assigned the highest weight, 40%, because protecting human life is the top priority. Other factors like mission impact, resource usage, and time constraints are important but secondary. This weights guides structured decision-making under pressure, enabling commanders to make rational choices quickly. Commander assigns scores to each decision option based on 4 criteria. The scores range from 1 to 5, where 5 indicates the most favorable outcome. These evaluations are made using available data, experience, and mission priorities. For example, continuing the EVA scores high on mission and time efficiency but low on crew health. Aborting the EVA improves health safety but sacrifices mission progress. Initiating treatment on-site offers a compromise but consumes resources and delays the timeline. The structured scoring helps the commander make rational decisions under pressure. In these scenarios, commander chooses to abort the EVA. The final MCDA scores were continue EVA 3.2, abort EVA 3.2, and initiate treatment on site 2.6. And decision was made on structured MCDA evaluation, which balanced 4 key criteria. Although continue EVA had a high score in terms of mission efficiency, it posed significant health risk. Abort EVA matched this score but offered a safer compromise, prioritizing crew health while maintaining acceptable resources and time impact. This example demonstrates how structured decision-making supports rational choices under uncertainty and pressure. Although this case study was only hypothetical, it was designed to reflect realistic challenges faced during analog space missions. This scenario showed how structured decision-making could improve response time and reduce uncertainty, even with limited or conflicting data. It emphasized that importance of robust data validation and demonstrated how medical decision framework could be effectively adapted to space mission context. This highlights guide and future development and testing of decision support system in real analog environments. Medical decision support system offers several benefits when applied to analog space missions. They enable faster and more reliable decision making, which is crucial in time-sensitive scenarios. Crew safety and health outcomes are improved through structured analysis and prioritization. The systems enhance autonomy, allowing astronauts to make informed decisions without constant ground support. They also provide tools to handle data anomalies effectively, reducing uncertainty. Most importantly, they leverage proven frameworks from medicine, ensuring robustness and reliability. The slide outlines potential direction for future innovations and collaborations. They are not personal commitments, but rather opportunities I see for the broader community. Broader community could develop decision tools tailored to analog mission needs, ensuring practical relevance, or open sharing of datasets and simulation results, which could accelerate collective progress. Workshops focused on decision making in extreme environments would foster knowledge exchange. Finally, these approaches may have valuable application not only in planetary exploration, but also in Earth-based crises such as disaster response or remote healthcare. To summarize, analog space missions share many decision-making challenges with medical environments. Medical frameworks provide robust solutions that can be adapted to space context, and structured decision support systems enhance mission success by improving reliability and autonomy. Future work will continue to expand and refine these methods, ensuring they met the evolving needs of space exploration. Thank you so much for your attention, and I look forward to your potential collaborations. Bye.